Let h be a function having derivatives of all orders, so it's infinitely differentiable. Selected values for h are in the table. Function h has the first four derivatives are increasing on the interval 1 to 3. Write the first degree Taylor polynomial h about x equals 2 and use it to approximate h of 1.9. Is this approximation greater or less than h of 1.9? Explain your answer. Okay. So, what do I want to do first? Write the first degree Taylor polynomial. So, step 1, write the approximation. Okay, come on. H of x is approximately 80. Where in the world did I get 80? That's h of 2, right? Plus 128 times x minus 2. And that's it. Agreed? H of 1.9 is approximately 80 plus 128 times 0.1, negative 0.1.
So it would be negative.
Yeah, 1.9 minus 2.
So it would be 80 minus.
Right, 67.2. All right. Then it says, is this approximation greater or less than h of 1.9? Any ideas? Why?
Because the next term is positive, so we'll add on to it.
Not necessarily.
So what is the
Use the range, and we can do
increasing in value, so it's less than.
it is less than, but it's for different reason.
It is less than. I agree that it's less than. It's actually, and this is a weird problem. Didn't they pretty much just have us write a tangent line? Isn't this a tangent line? A first degree Taylor approximation is a tangent line approximation.
And then you know x is positive.
Function is concave up. Tangent line falls below. Weird question. I think that's a weird question. But h prime is increasing. Therefore, h double prime is greater than 0. Concave up. So 67.2 is less than h of 1.9. I thought that was a weird question because you did want to use a Taylor, like error bound or something, and all you needed was a normal tangent line thought process. Write the third degree Taylor polynomial and use it to approximate h 1.9. By the way, this was a calculator problem. Okay, third degree Taylor polynomial, I've got part of the way there already. And then I need the third, I've got the table sitting here, 488 over 3. X minus 2 squared over 2 factorial. Plus 448 over 3. Man, my brain really wanted to make that 88. X minus 3 cubed over 3 factorial. Oh, you're right. Thank you. and then use that to approximate h of 1.9. Use a calculator to plug that in. I'm going to cheat for you and tell you the answer. No, you don't. You can, right? Nobody's like, I couldn't have done that. Right, you got that. It would take you a minute.
Let's just plug it in and not actually do anything.
Mm-hmm.
So it's actually 0 over 2, which would be 1 over 100. So that actually 200.
Oh, this?
I'm actually looking at it.
Oh, good luck with that.
It's not that bad. It's just big.
Yeah. Use the Lagrange error bound to show that the third degree Taylor polynomial for h about x equals 2 approximates h of 1.9 with an error less than 3, 10 to the negative fourth. So I'm going to do a Lagrange error bound. Remember, we're going to do the derivative, the maximum value of the derivative on the interval. Well, what do you know about the derivative? Increasing from the interval 1 to 3. Very good. Couldn't we just go to 3 and know that that's the most it could be? Well, and really you could even go to 2 because you're under 1.9 is under 2. You could even go to 2, couldn't you? Because h of 1.9, we know that the derivative of h of 1.9 is going to be less than. But yes, either one of these. That one's plenty. That right? Because we're looking at. We're trying to approximate h of 1.9. The highest the derivative could be between 1.9 and 2. The highest it could be is the value at 2. The derivative, because we're looking to approximate h of 1.9. So now the closest one that's greater. Right, it's got to be greater. But it is a safe bound because I know 2 is greater than 1.9. So between 1.9 and 2, the most the derivative could be.
So we can change it.
Yes. You could also pick the other one. Now, there is no guarantee that the other one works, but will someone work it with the other one? I'm just curious if it works too. Someone work it with the. It wouldn't matter, but I mean work it with the 3. The 1125 over 16. Someone do the same work I'm doing except with the 1125 over 16. There's just a chance it's not small enough, but yep. 1.9 minus 2 to the 4th power. Why am I doing 4th power? The next term, right? The one right after. Remember, this is the largest value the derivative could be on the interval. Since we are from 1.9 to 2, the largest the derivative could be is at 2 value. You think you got it? Bring me the key.
So if we don't have a table that's set like that, how do we know?
It's got to some way give you a way. Now, some of them flat out say the most the derivative could be here. Now, I helped someone with a homework question, and the derivatives were sine and cosine. Well, you know those are always trapped between -1 and 1. So the greatest the value could be is 1. So somehow there's going to be a way that you can find a safe bound for that derivative. And found the maximum of it, yes.
What
If it's a function.
I got is 2.930 times 10 to the negative 4.
That will work, won't it? No, wait. Say what'd you say again?
2.930 times 10 to the negative 4.
That works.
So
It's safe. So it would have worked. So you could have used that one and you would have been correct as well. The only danger in using, you could always use one too big. You just may not be able to get in the error that they're trying for you to show.
So alternating doesn't actually have to be altering.
No, we're not doing an alternating series test. We're doing a Lagrange. So I don't care if it's alternating or not.
We're talking about the 3.
Yeah. We're just talking about. Will you put that back for me? We're just talking about the Lagrange error bound, and so I used the 2 when I worked this before I came in. I used the 2, but you could have used the 3, and it would have been safe as well. And what is this one? This is 2.7037 times 10 to the negative 4th. If you had used the other value for the derivative, which is also fine, you get a value that also works, which is less than 3 times 10 to the negative 4th. We get out at 25. I will look.
Okay.
25. Yes, 25. So I still got closures. Okay, any questions about that one?
In alternating series, the thing that you want to do is that just the radius of the functions.
Alternating series. No, you plug in the x value. You plug in the x value that you're evaluating. So at 1.9 or whatever. That's okay. We need to do 3, right? Okay. All right, last one. And then I will be done. Teach it. You will be done hearing me teach forever. Sort of. Do what?
I said I should take tests.
Well, like formal teaching.
You're gonna haunt us in our heads. Like,
Maybe.
what she said.
We've got a lot of prep work to do, so you'll hear me talk a lot. But as far as a lecture, this is. So you're a little sad, aren't you? I know you. Just a little. Okay. I understand. It's okay. All right. So read this one. See what you can come up with. All right. So cosine. Okay, write the first 3 terms in the non-zero term of the Taylor series of for cosine of x centered at 0. So, why am I making you take that mastery exam? So you can do this without having to do all of those derivatives.
Let's think about it. I can do this.
Well, I did, didn't I? I had it paused.
Yeah, I know. I wasn't thinking about the problems.
So this will be something on your mastery exam tomorrow. That's the first 3 non-zero terms, agreed? And the general term. Now, if you don't have it memorized, let's think it through. When I plug in 1 for n, or you could start at 0, it doesn't matter. The general term can start at n equals 0 or n equals 1. It's whatever you make it to be. You know what I mean by that? We do need an even value, right, for x. Now, if I do this, would you agree I have to be starting at n equals 0 to make this work out? Again, it doesn't matter if you start at n equals 0 or 1, as long as your general term matches what you're doing. Good. Divided by 2n factorial. And what's... It would, because then it would just be the n factorial multiplied by 2. One other piece, what else needs to happen? It needs to alternate, so we need to put an alternator in. You can either do -1 to the n or -1 to the n plus 1. It depends on whether you started at 0 or 1. Since we started at 0, -1 to the 0 power is +1, so it starts correct and alternates appropriately. Any questions about that part? Use this to write the first three non-zero terms and the general term for the Taylor series for f about x equals 0. Well, I know f of x, the top part of f of x, which is the part I need a series for. I don't need a series to write negative 1/2. So I'm going to take this big thing and subtract 1 from it, right? What happens if I subtract 1 from it? The 1 in front goes away. And then I'm going to divide every term by x squared. Everyone agree with that?
We actually have to if we plug it into
What?
all over x squared or takes like that.
Yeah, probably. But the general term would be quite difficult. Probably. Oh, did I? No, I'm doing that right. How many terms do I need? 3. So I do have to add an additional term. Do you agree with that? It would be x to the 4th over 6 factorial. General term. We still need our alternator. Whoops. Negative 1 to the n still works fine, but if I am doing negative 1 to the n, then would you agree I'm starting at n equals 1? If I want to start back at 0 again, I'd have to do minus 1. We'll see. We can change it if we need to. X, if I put 2n factorial on the bottom, would you agree I'm starting at n equals 1? Because then I've got 2 factorial, 4 factorial. What would need to be the exponent? 2n minus something. Let's try it. What if I plug 1 in for n, or what did I say? 1 was where I started, right? If I plug 1 in for, I would get 2. What do I want to get? 0. So 2n minus 2. Let's check and see if it works. This would be n equals 2. 4 minus 2, which is 2.
So that's right.
So how do you say if you're starting at n equals 0?
You don't have to say it, just has to be right. Like consistent. As long as this works.
So it doesn't have to be consistent with your previous answer?
No. You can make a general term that's any pattern. Now, if you do go ahead and write the sum, then you have to say n equals something. But you can start it anywhere. But what I mean by consistent is I can't have the 2n, n being 0, and the 2n minus 2, n being 1. You know what I'm talking about?
They just have to figure out.
You just have to figure out a pattern. You don't have to have any specific n you start at. Okay.
So can you figure that out?
We hope so. Now, most of the time you're going to start at 0 or 1, but, I mean, you know. I think it'd be harder to start at 5. But I'm not saying no. Yeah, you could. Okay, B. Use the Taylor series for f about 0 and found in part A to determine whether f has a relative maximum, minimum, or neither at 0. Give a reason for your answer. Okay. How am I going to do that? Okay, good. F prime of x, which is 2x over 4 factorial. Where did the 1/2 go? The derivative of a constant is 0. 4x cubed over 6 factorial. Correct. 6x to the 5th over 8 factorial. Equals 0, add x equals 0. Everyone agree with that? So that's a first derivative. The easiest way on these Taylor polynomials are going to be a second derivative test. The second derivative is 2 over 4 factorial minus 12x squared over 6 factorial. I don't care about the rest when I plug in 0. F prime, double prime of 0 is what? Which is positive, which means I'm concave up. Agreed? So it is a minimum at x equals 0 by second derivative test. Fifth degree Taylor polynomial for g at x equals 0. Before I go on, any questions about the second derivative test? It's been a while since we did that. Okay, so on the first derivative, I set it equal to 0. And since it all had x's in it, that will equal 0 when x is 0. The second derivative, I did the derivative of all of that. You okay with that part? And then I plugged 0 in for all the x's, which is just going to leave the term without an x. And that term happens to be positive, which means my function is concave up. And if I have a concave up function, I have a minimum. If it's a critical point, which it is, I showed that here, then I have a relative minimum. Fifth degree for g, which we actually have to go back and see what g is. G is the integral of 1 plus, or sorry, is 1 plus the integral from 0 to x of f of t dt. Right? So I'm going to rewrite f of x down here just so it's handy. You already have this somewhere. Negative 1/2 plus x squared over 4 factorial minus x to the 4th over 6 factorial. I think that's good. I think I could stop there. Why is that a good place to stop? True. And what's going to happen when I do an integral? What's a 4th power anti-differentiated? 5th power. So I know I'm safe stopping there because this is about to be a 5th power. It's not yet, but it's about to be. Remember, that is a notational technicality. Yes. When you do an integral, you can't go from 0 to x as your endpoints if your variable is x. So it's just a technicality on that integral to make it where you can do an integral. So g of x is 1 plus the integral from 0 to x of f of t dt, which I know is the antiderivative at x minus the antiderivative at 0. Just note that you don't need to write that, but that's just a mental note. Agreed? Everyone agree that's how you do that? Would you agree the antiderivative of this at 0 is just 0? Because everything will have an x in it, so that will be 0. So I'm really just looking for f of the antiderivative at x. 1 plus antiderivative of negative 1/2 would be negative 1/2 x. Antiderivative here, add 1 to the exponent. X cubed over 3 times 4 factorial. Everyone agree? Minus x to the 5th over 5 times 6 factorial. I think that's a 5th degree Taylor polynomial for g. Is this helping with some homework questions as well, even though we're not manipulating these things around? Alternating series, right? G is an alternating series. So the error is less than the next term. Everyone agree with that? Which is, we do need to write the next term, the negative, yeah. It's negative, right? It's to the fifth node. Oh, wait. It says the third degree actually, I'm using the fifth power one.
Oh.
Because it says, so they're not even making me find another term. So first I have to find T of 1 using the third degree. So I stop here.